Hello, this is Derek Longshore. This is the Shuttle Vehicle and Autonomous Architecture portion of our final project. Here you can see the vehicle specifications that we found from Tesla's website online. We had to make some assumptions such as that the vehicle was not going to have any passengers so that we didn't have to have a variable mass. And then we also went ahead and assumed the sensor's height and weight was going to be negligible. Here is a table of the sensors that we used. Here's a picture of how the sensors would be situated on the car. And here's a map of the sensors showing the layout of where the sensors were going to be covering and the range.
Hello, this is Ifan Wu. I will introduce our low-level longitudinal control for our model. Here are the parameters and equation for the model. Here are the vehicle specifications. We use 3000 seconds for the duration of simulation. There are 6 inputs. First input is first torque input, then coast down input, second torque input, brake input, and wind resistance input. Also the road slope input. There are 3 major speed limits in eastern area. So according to each of the speed limits, we have the velocity for the vehicle when it's in 15 miles per hour, 25 miles per hour, and 40 miles per hour. Here's the second torque input response when it's accelerating from 15 to 25 miles per hour. Here's the 25 miles to 45 miles per hour. Here's the 15 miles per hour to 45 miles per hour. We also have coast down for the 3 cases, and we add additional brake force to the model at 3 speed limit. We also can see the wind distribution impact at 15 miles per hour can stop the car, but it will slow down the car in 25 miles per hour and 45 miles per hour. The road slope is a big impact on the speed of the car. As slope increase, the car slow down more rapidly, and finally it will stop.
Hi, my name is Shihao Liu, and today I'm going to introduce the low-level lateral control mode of our systems. These are the parameters we get for the Tesla Model X, and the equation used for the model is shown in this slide. The nonlinear lateral control model is made up of 4 parts: steering angle projection, kinetics, dynamics, and the tire model introduced in the previous parts. The linear model is built based on this equation shown in the slide, and the slide also shows the diagram of the linear model. Here is the screenshot of our Simulink mode, and a saturation is added to maintain the steering angle within the limitation. The limitation is calculated from the smallest turning cycle we got for the Tesla Model X. Before the team Simulink the test part, the team Simulink the yield rate versus different speed with this code. And from the result, we can see that the velocity is and the steering as long as its speed is less than 295 miles per hour. So use this model, the team Simulink, with the simple part of this test path. The path is made up of a quarter circle and a straight line. The steering angle is calculated as 0.68 for the turning parts. The speed limitation is 6.83 meters per second, and the turning parts is quite sharpened, so the team set the velocity desired to 3 meters per second. And this is our simulation result. So from the for the model rear angle, we set the 0.68 for the first 30 seconds, and then it will become 0. And it took about a second for the slip angle to settle down for the nonlinear model, but the linear model gets stable almost immediately. And it takes about 24 seconds for the yield rate to settle down, while the linear model also get stable immediately. So the maximum velocity we get is higher than the desired velocity, but is still lower than the legal speed limitations.
My name is Taewon Han. My part in the project is path planning and following. This is the model created for PID tuning, and it was the part of previous homework. I set the constraint and condition as you can see in below, and I obtained the PID gain from that model. Given the project map, I obtained the real coordinate from the Google Map. However, Google Map is using the longitudinal and lateral coordinate system. So I transformed that to UTM coordinate, which unit is a meter. And I implemented 13 segments of Bayesian curve for the path following. I tried to make the smooth curves in the Bayesian curve. So I implemented the genetic algorithm, and as a result, the maximum differentiation of curvature in the path is less than 0.015, which is very smooth. I added the feed for the computation part into the path following model, which was given in previous homework, and I implemented the velocity for 2 meter per second velocity and 10 meter preview length. As a simulation result, there is very small steering error. However, the position error is really huge. This is because the steering angle is accumulated over time, resulting huge position error. Currently, controller is just following predefined steering angle over time. However, if we are using the perception result to do localization, then we can get more control input to compensate that kind of error. Thank you.
Our autonomous shuttle will be equipped with a collision avoidance strategy. This following simulation shows the collision avoidance strategy being deployed with the longitudinal model for the vehicle discussed earlier. The simulation could show a target vehicle at a red light, or a vehicle dropping off a passenger at the shopping mall, or perhaps a pedestrian crossing the street in front of our autonomous shuttle. The results show that the target vehicle became visible at about 40 seconds. Shortly after, it became in range within our autonomous vehicle's sensor set. At this point, the decision-making strategy could determine the best way to ensure safety for the autonomous shuttle and its passengers, in which case it applied a braking force to descend the autonomous shuttle down to the speed of the target vehicle, in which case was 0 meters per second. Localization and perception. Our autonomous shuttle will utilize GPS and an IMU, which can be modeled using the third-party GPS navigation toolbox, as well as MATLAB and Simulink models, such as a gyroscope and an IMU. Our car will also utilize a neural network toolbox to deploy quick state-of-the-art detection algorithms, such as convolutional neural networks. These can actually be deployed to an NVIDIA GPU on board using the GPU coder. We will also use heat map filters as well as optical flow using the computer vision system toolbox to actually track objects as they move about the screen. Finally, sensor fusion and ranging can be used to gain real-world insight into the vehicles on screen, such as their range and relative velocity to our autonomous shuttle.
Hello, this is Derek Longshore with the Stateflow decision-making portion of our final project. Here you can see the picture of the route the trolley would take and also the autonomous vehicles would take since we were replacing the trolley. The picture on the right shows all the stops that the vehicle has to consider. Here's the finite state machine. In the convenience of time, I won't go into great detail, but I do on the next slide. But just some highlights are the vehicle following is when the vehicle is following a vehicle or there's a vehicle ahead. Path point following is when there is no vehicle in front and the lane or road is not detected. Lane keeping is when there is no vehicle ahead, but it will still follow the lane or the road. Obstacle avoidance is when there is a obstacle detected in front and has to find a way around it, while stop and wait is when there's a traffic signal or emergency situation where the vehicle needs to come to a complete stop and wait. I also did the real-world implementation challenges. Some of the challenges and some of the highlights of the challenges and their risk level are the snow and ice road conditions versus low visibility weather, fog, or heavy rain. I think the snow and ice road conditions are a higher risk than just rain or fog, since the vehicle should be able to operate even in low visibility with the different sensors it has, while snow and ice causes problems with braking and just traction altogether, so that's a higher risk, and the vehicle would have a harder time understanding the snow and ice conditions. Pedestrians crossing the road in unpredicted ways has a high risk due to the risk to the pedestrian. If they get hit by an autonomous vehicle, it would cause a lot of problems, as well as it could cause the pedestrian to lose their life. There's some others as well, medium level ones being like street sign vandalized or missing. It would be a medium risk if the vehicle didn't realize there was a stop sign or something, but as long as the vehicle knows the route, since it's preset, it should still come to stop at signs even if there is no sign there.